Hi, welcome to Module 2, and today we'll be looking at how to declare variables, specifically local variables. We'll be looking at how we get input from a Windows form, so at runtime when the user wishes to provide data to a running program, you'll see how that can be entered through a Windows form. When data is provided to a program at runtime, it may be necessary to change the way the data is stored internally or to do a data type conversion. So we'll look at what data types are and what is done to convert from one data type to another. We'll take a look at how arithmetic and string operations are processed. And we will show how to take data that has been processed by a running program and display it through a Windows form. So before we get started, I want to provide some background information that I think will be useful, and this way as we study programming you'll have some conceptual understanding of what's going on under the hood. First of all, and I mentioned this in the previous lecture, but I'll review it again. First of all, you need to be familiar with the idea of language translation. And language translation is done a little bit differently in .NET than what I'm going to describe here. And we will eventually look at how .NET actually translates the program statements that we write into executable code. But the basic idea, and this applies not only to .NET programming languages but all programming languages in general, the basic idea is that human beings will examine the environment in which they're working, will determine the steps that are necessary for a computer to follow in order to solve some real-world program, and then will express the solution to that problem using what's called a high-level language or source code. And in our case, we're going to be using C# as our source code high-level programming language. So the human being would understand the problem, write the solution to the problem in a language that's very English-like. And as we pursue this topic, you'll see what I mean, that the C# programming language has characteristics of the English language. So a programmer would begin the process of providing instructions by writing in a high-level language, or in other words, the source code. And at some point, once the instructions have been entered in through a text editor, something somewhat like a word processor, then the programmer would in some way provide a command to tell the system to take the English-like source code statements and translate them into a binary format that can actually be understood by the computer's hardware. So the program that's used to translate from high-level source code into executable code is called a language translator, and there's a couple of ways that language translation can be done. Most of the time it's done using a program called a compiler. Now, the compiler that we use is built right into Visual Studio. So to invoke the compiler is a very simple thing. You just point and click at an icon on the toolbar, and it will automatically then take whatever program code you've written, do the translation, and begin executing it. So once the high-level language has been converted into a binary format, and there's some other things that go on in the process that I'll largely ignore here, but it's the program code that you have written has to be combined with certain other pre-written program code that's contained within libraries. But once that executable code has been created, the combination of what you've written along with the program code that's merged from libraries, that executable binary code then is given to the central processing unit, and the central processing unit is the computer hardware component that has the ability to interpret the instructions in binary format and then signal to the rest of the hardware how to carry out that instruction. So the CPU requires that your program solution be translated into a binary format before it can actually carry out the task. All right, so that's a quick overview of language translation. And next I want to, just for background, I want to provide you with a diagram here that depicts what is known as the von Neumann architecture. So you can read about this from online sources, but computers have been built according to this design since really the end of World War II. And whether it's a desktop computer or a notebook or a tablet or even a giant supercomputer, they all have basically the same architecture, and it involves a hardware component that acts like the brains of the computer, which has two component parts: one that can read, that can interpret the binary code that it's been provided, that can read the software, the representation of the software in as a sequence of high and low voltage states. And then there's also a component that performs the arithmetic and logic operations that are required to do anything from crunching numbers that are required in a problem solution to generating graphics so that certain representations and images can be displayed on the screen. But this hardware component is known as the central processing unit. And again, the central processing unit contains two component parts: the control unit, which reads the binary form of program instructions, and the arithmetic logic unit that performs any arithmetic and logic operations. So the CPU acts as the brains of the computer. And if you buy a computer and you see a sticker on it or something that says Intel inside, that's a reference to the computer's CPU. So there's a company called Intel, not the only manufacturer of CPUs, but certainly the largest and most widely known. There are companies that are in the business of making this particular component part because it's so fundamental to every computerized device. So your Intel processor is an example of the CPU. Now, just like in the human brain, part of the activity that goes on is the activity of processing, or taking what is known about something and formulating new ideas. That part of it in the computer would be handled by the central processing unit, but there's something also analogous to what humans think of as memory. In human beings, we are familiar with the idea of short-term memory and long-term memory. The computer system has something very similar. When a program or the data, that would be the numbers and the character strings and whatever else might be used for processing purposes, when program instructions and data are actively being executed, when a program is in an active run state, then the program instructions and the data that the program uses is stored in the immediate form of memory, or what's known as primary memory. And we think of that type memory most generally today as RAM memory. Now there's some other, physical forms that can be used other than RAM. You have something called PROM and EEPROM and so forth. But this is short-term memory where program instructions and the data that they use are stored, and those instructions are fetched from memory and processed by the central processing unit. In the simplest form, an instruction is fetched, it is decoded, it is executed, and then the next instruction is fetched, decoded, and executed, and that process goes on and on and on at a very rapid pace, but nevertheless, in the most basic form, the program instructions are fetched one at a time, carried out by the central processing unit, and then the next instruction is fetched. Now, there's a lot more to that I'm glossing over, but this gives you the basic idea, the basic background. So as the program runs, it's stored in memory, in primary memory, and its individual program instructions are executed by the CPU. And when program instructions are needed by the user over a period of time, they can also be stored in a long-term storage, which is known as secondary memory. So disk memory, flash memory would be examples of secondary memory. CDs, DVDs, other examples of secondary memory. So generally, when you work with a computer, you have your hard drive, a disk that acts as secondary memory, and it stores a number of programs to include the operating system, or the programs that collectively make up the operating system. And when you turn your computer on, those program instructions, the essential ones, the operating system instructions, are immediately copied into primary memory during the boot up process, and at some point, once they execute, the computer transforms itself into a familiar device. You, for instance, might see the Windows Start menu. And at that point, if you want to use some other program that you've purchased that's installed on the computer, you would typically go maybe to the Start menu if you're using a Windows computer, click on an icon, and that would signal to the operating system to ready the hardware and begin the process of loading additional program instructions into memory so that they can be executed by the CPU. And so, depending upon how many programs and what programs you have installed on the hard drive, the computer can, continue to run different program instructions and transform itself into a variety of different things. It can act as a word processor on one occasion, act as a gaming device on another occasion, and it's the same hardware that just happens to be using different instructions to perform various tasks. So secondary memories where program instructions and the data that they use are stored long term. When they're needed, when you actually need to run them, they have to be copied into primary memory. Once they're copied into primary memory, the program instructions can be fetched individually and decoded and carried out. And from time to time, as a program runs, there may need to be input from the user through some device like a mouse or keyboard or whatever the input device might be, microphone. And so supplemental data can be given to the computer at runtime. Also, when the computer runs the program instructions, there is typically a need to show the results of the processing of the data. And so this final element in the von Neumann architecture, the output device, would allow a user or some other system to be able to see the results or use the results of the data that has been processed according to the program instructions that the computer's been provided. All right, so hopefully that's helpful. That is the von Neumann architecture, the basic hardware components and how they interact with each other. Another useful way of looking at the computer is to look at how the hardware is influenced by the software. So again, the hardware sits there with the capability of doing things, but until it's given an instruction, it really doesn't do anything or can't do anything by itself. So where do these instructions come from? Well, as I mentioned previously, there are a collection of programs known as the operating system, and then there's some additional programs that would fall into this innermost category of software known as system software. So you'd have the operating system as the core component of system software, but we might also include antivirus software and some utility programs that are used to either enhance or otherwise improve the performance of the hardware. So if you see an ad on TV for PC-Matic or something like that, or registry cleaning software, those would all be examples of system software. So you have a layer of software, of a category of software whose purpose it is to either control or to improve or optimize the performance of the hardware. And so we can think of any program that falls into that category as system software. And then we also have another broader category of software called application software. So just about any kind of program you can imagine that is useful to you as a human being in the real world would be an example of an application program. So, you know, as I look down here at the taskbar, for instance, I see a shortcut to Windows Explorer, an application program, to Camtasia, which is what I use for screen recordings, and the various shortcuts that I have set up for Microsoft Office, my browser, and a variety of other software that I use, and just to, you know, improve my life day to day as I use the computer would all fall into the category of application software. So a couple more things to be noted about this, and I don't want to, you know, spend forever on it, but in this class our focus will be on developing applications. So we're not writing system software, we're writing application software. And should also be known that when applications need to affect the hardware, so for instance, if you need to save your word processing document, or if you need to open some other file that's stored on the computer's hard drive, the application has to communicate a request through the system software, which in turn controls the hardware, or which in turn will communicate that request to the hardware. So it is a layered type of approach that's used, and as we, you know, develop applications, we'll be developing them, and they will have the ability then to communicate through the system software to control the hardware in whatever, you know, manner we want to influence the hardware. All right, so that's a way of imagining what's going on under the hood. Another diagram that I want to bring to your attention before we really get into the nuts and bolts of programming is a diagram that shows the input-output cycle. So this is really computing in a nutshell. So if I had to describe to someone in the quickest and the way possible and use the least amount of time and words and so forth, I'd probably tell them that here's the basic idea behind computing. You have a platform, okay, the hardware that has access to program instructions, and those program instructions tell the hardware what to do, and from time to time the hardware as it's directed by the program instructions will require data, names and numbers and so forth, and that raw data then can be input to the running program. The running program will process it in some way, shape, or form, and then output the results and provide the user with value-added data, or in other words, information. So you can think of as raw data as being kind of the finish. The raw material that is processed in order to create the finished product, which we call information. Okay, so that's really computing in a nutshell. And the other diagram that I want to review, and this was discussed in class last time, and I can't remember whether I included it in the video for Module 1, but certainly I discussed it in class last time. This diagram describes the way programs are created, the model by which programs are created, the object-oriented programming model. And what you need to understand pretty quickly is that we will be writing program code, and for the most part in the CS1 course we will use program code that many program modules that have been developed by Microsoft that are just available to us out of the box. And these modules or components that we're going to be using that have been pre-written are known as classes, and you can think of them as being somewhat like a blueprint. And so if we want to build something, we will find the class that is appropriate and make a working copy of it. We will instantiate the class, so the term that's applied is to instantiate. So at the time the program runs, an instance of or a copy of that blueprint will be provided to the program, and that working instance is known as an object. And objects have two major components: properties, which are their attributes, and methods, which are the actions that they can perform. And again, I'll discuss this in more detail. You haven't heard the last of this, but you should be familiar with this model and have some idea that classes are the blueprints from which we create the working objects, and those objects have things about them that we can manipulate, their attributes, and they also have methods that we can employ. All right, so I'm finished with this diagram, at least for the moment, so let me move on to something else. And that something else is going to be my third document that I'll provide to you in the class folder. And this is just a quick summary of C# language statements. Now, learning how to program can be, as I explained last time in class, can be a pretty rough experience the first few weeks, because you have to get familiar with the development environment, the integrated development environment, in our case Visual Studio. So you have to understand how the software works and how you create a project, how you save a project, how you retrieve an existing or previously saved project. So there's lots of details that you have to master immediately about the tool you're going to use. And then you also have to very quickly develop some core understanding of the language that you're going to be working with. So if you think back to the diagram that we looked at previously that related to language translation, we write in a high-level programming language called C#, and that programming language has to be translated by a compiler into a binary format in order for the computer's processing component, the CPU, in order for the CPU to carry out whatever task we intended. And if we don't write the instructions correctly, if we create what's known as a syntax error, then the language translation process breaks down and we can't provide the instructions to the CPU. So starting out, it's going to be a bit of a struggle trying to develop your skills writing in this new language. But you just need to be patient with yourself and hang in there. And so I'm trying to make life a little easier for you by providing you with a quick summary of the key elements of the language that you need to work with. And so as we proceed here, let's talk about something that's very, very fundamental to programming, and that's the idea of a variable. Okay, now you recall from the von Neumann architecture that you have a component called primary memory, and in primary memory we store program instructions and the data that the programs use while the programs are actively being executed. And so my point here is that when a program is actively being executed and it needs to manipulate data, how does it find that data? How does it keep track of the data? And the answer to that is it stores the data in something called a variable. And I've provided a couple of definitions here. One that I just very rapidly found as I did a Google search. Okay, I'm not sure this is the ultimate definition, but hey, I just wanted to show you that if you can't quite wrap your head around this and you want further explanation of what a variable is, go online, Google for, defined variable or something, and there's lots and lots of information that you can read through. But I'm going to use my definition here, and so what I want you to understand is that a variable is an identifier or a name that is created by a programmer. Okay, so who comes up with these variables and variable names? Well, it's the programmer, the person that's writing the instructions. And there's some very specific rules that are required for naming variables. And I'll mention those later on, but just understand for the moment that when you want to have your program work with stored data as it runs, you have to provide these containers, these references to memory locations, primary memory locations. You have to create the variables, you, the person writing the program instructions, or in other words, you, the programmer. So they are programmer-defined identifiers that reference data storage locations in primary memory. Okay, so that was my reason for wanting to very quickly show you the block diagram that describes the von Neumann architecture, so you'd be familiar with this component part of the computer called primary memory. So these names that we create to reference stored data are really pointing to memory locations in primary memory. And in those locations, we have the ability to, within our program instructions, to assign data to them, to put data into them. We also have the ability to read from them or take data out of them. And that process of putting data into something is known as a write operation in general, and taking something out, or taking a copy of what's stored is known as a read operation. So the programmer has the ability to read and write to these storage locations. Now, some other things that you need to catch on to very quickly is the idea that the storage locations can be formatted differently depending upon what the data is going to be used for. If the data is going to be used for arithmetic purposes, it will be formatted in very specific numeric formats. Could be integer, could be floating point, could be type double. And if the storage location is going to store a signal as to whether something is one state or the other, we might format it to store a data type known as bool, a true-false data type. If the storage location is going to store data that's going to be used alphabetically or alphanumerically, then we might format it as type string. So again, depending upon what we're going to do with the data, we'll create variables or references to memory locations, and we'll format those memory locations in a variety of different ways. The ways that we will format those memory locations in this class, and this is not an exhaustive list of the type formats that are available, but this is what we'll use in this first computer programming class. We will use a format called int if we want to store away whole numbers. We'll use a format called double if we want to store away numbers that have a decimal component. We'll use a data type called string if we want to store alphabetic or alphanumeric data, and we'll use a data type called bool if we want to store away true or false. And incidentally, that should be lowercase t. Thank you, Microsoft Word, for changing that. And so in our program, when we write our program instructions, we will have to account for all the storage locations that we want to use to store data, and we will have to give them some kind of meaningful name. We'll have to specify the data type format that we want to use, and then depending upon where we declare the memory locations, where we declare these variables, we will affect how long the variable is able to store value, and we'll also be able to affect where that value can be used within the program. So lifetime has to do with what it sounds like, how long data is stored in a memory location in a variable, and scope has to do with what parts of the program can have access to it. Starting out, we're going to be working with what are known as local variables. They will be variables that are created, otherwise known as declared. There'll be variables that are declared within methods. They will be used only within the method in which they're declared. That would be their scope. And they will only exist as long as that method exists, and that has to do with their lifetime. All right. And I show you a number of ways in which we can declare a variable. So I mentioned before that if we're going to store data, if the program is going to process data and we need variables, then we have to account for these things. We have to create them, we have to declare them, and there's a very specific syntax that's required. You have to specify the data type, then you have to specify a variable name. Now there's some variations on how we can do this, but then the sentence needs to terminate with the statement needs to terminate with a semicolon. So data type, variable name. Now notice the way I've named these variables. I'm using something called camel case notation. I believe I mentioned that in class previously, but you know, if you smoke something funny and look at this, you might imagine that that's the camel's head, and that is the first hump, and that is the second hump. So one of the rules that you have to abide by in creating variables is that you cannot create a name that contains embedded spaces. Now all your life you've been taught when you create a sentence or even a phrase, you need to separate words with spaces. Well, you can't do that. The language translator is going to not understand what you're doing. It's not going to translate. You're going to get a syntax error. So a way to make the variable names that you're creating easier to read is to start out and name them something descriptive, a little phrase that describes what the variable is being used for, and create the identifier in such a way that you start out in lowercase, and then as you introduce a new word to the phrase, bump up the first character of that new word to an uppercase character. And it makes it pretty readable. That, again, is known as camel case notation. So it's not an absolute requirement that you create your variables in camel case notation, but that's the way I'm going to do it. That's the way most professionals do it, and so it's a good idea as you're learning to do it that way. So here's an example of us saying, okay, language translator, we are going to set aside an area of memory. You go figure out exactly what that address is, but we want a chunk of memory. We want it formatted to store whole numbers, and I don't really care what the actual memory address is in the computer's RAM, but anytime I want to reference that memory location, I won't use the actual address. You'll have to figure that out. What I'm going to do is use this identifier called your birth year. Your birth year is going to be associated with that same memory address over and over again throughout the lifetime and scope of that variable. And in this statement I say, okay, language translator needs another chunk of memory, make it, formatted for a whole number, and call it something different, call it my birth year rather than your birth year. And by the way, go ahead and put into it the value 1,954. No commas or any of that stuff, just the numeric value. So here's an example where I declare a variable and initialize it. The term that's used is initialize it, or I give it an initial value. That's perfectly legal. I do the same kind of thing here, except I want it formatted in a way that will support a decimal component. I create another memory location, don't assign it anything, but tell the language translator, hey, give me a chunk of memory. I'm going to store alphanumeric data, hereafter known as string data, and I'll call it name. When I want it, I'll refer to it as name. And again, more variables. I want to show you a couple here that are very important. This one right here is declaring a variable called birth year, and looks like I kind of messed the spelling of that up a little bit. So we'll pretend it says birth year. And I'm assigning it whatever is in text box 1 on the form. So I'm using the contents of text box 1, the text property of text box 1, the object text box 1. But text box 1 stores data in a string data type. It's formatted for string. And what I want to do is I want to put this in a memory location. I want to get a copy of what the user's typed into that text box, and I want to put it into a memory location that is formatted to store whole numbers. So what am I to do? The actual contents in the text box is formatted for string. I want to get a copy of it and store it in a memory location formatted as integer. The way I deal with that is to use a built-in .NET object called convert that has a number of different methods associated with them. One of the methods that's associated with it is called toInt32. And when you call up that object and you invoke its toInt32 method, and then within parentheses give it something that translates into string, data type, that convert object will transform the string format, the value in string format, to the same thing in integer format. So this is how I have to get data from that the user has typed into text boxes stored away in a different format in a variable. And I do the same kind of thing down here, create another variable of type double and give it a meaningful name, percent change. And I again invoke that same .NET object, but this time I invoke a different method, the toDouble method, and I tell it to take whatever's in another text box, convert it to type double, and store it away in a memory location known as percent change. And finally, you can look through these examples down here. Down here I declare a variable called fName of type string, and I assign it the contents of text box 1's text property. So if I need to capture something from a Windows form text box and store it away in a variable formatted as type string, I don't have to do any data type conversion. It's only if I want to capture the user's input and store it in a variable of type integer, or I want to capture the user's input and store it away in a variable of type double, it's only then that I need to use that convert object. Also show you a data type called bool, and bool is used to store true-false values. Okay, so this is how I declare variables. You're going to see an actual example of how this is done in some sort of meaningful context here momentarily. But for now, I want to show you one other incredibly important statement, and that's the assignment statement. This is the most used statement in the language, and it always has this general form. Target location equal expression. Now, what that target location is can vary. It could be a control object on a form, it could be a variable, it could be any number of things, but that's where we want to put the resulting value. And then expression could be any number of things. That could be a complex arithmetic expression to do a calculation, or it could be something as simple as giving it a individual value, and I'll show you concrete examples here momentarily. In fact, we'll do it right now. So one of the things I might do in using an assignment statement is to store away the result of arithmetic operations. Now, I show you a number of statements. These are not intended to be used, collectively to do anything. These are just individual statements, just show you concrete example after concrete example. There's nothing meaningful about this in terms of it solving any kind of problem. All right, so in this example, what I show you is that if I have a variable previously declared, and if it has already stored a value, and I subtract from it another variable, the contents of another memory location, then I can take that difference and store it in yet a third variable, third memory location, which I call diff year. So I'm performing an arithmetic operation and assigning the result in diff year. Diff year is the target, and your birth year minus my birth year is the expression in this case. I have another example, completely unrelated to the first example, where I am taking some previously stored value in a variable called old price, and I'm adding to it that same value multiplied by some percentage. So if I want to increase the price of an item in inventory or something like that, I might take whatever the old price of that item is, multiply it through by 0.1 or something, and take that resulting sum and store it away as my new price, and that would be my old price increased by 10%. Now, notice some things here. The programming language uses some very specific arithmetic operators. You can read about this in the book. It uses plus for multiplication, minus for subtraction. It uses an asterisk for multiplication. It uses a slash for standard division, and it uses a percent sign for modulus division, which we'll talk more about later on. So in this case, I'm performing an arithmetic operation. One more thing I should say. When you construct these arithmetic expressions, so that's the expression part of this assignment, overall assignment statement, the arithmetic expression will follow the standard rules of algebra in terms of order of operations. So in this case, since I'm performing two arithmetic operations as part of that expression, then it'll perform the multiplication first, and whatever that resulting product is, it will add it to this other variable and then assign that newly computed value that results from a multiplication followed by an addition. It will assign that to new price. Okay, so you may want to read up on that. In this case, I'm performing a string operation. So we have arithmetic operations, we also have string operations. The string operation I'm performing with the plus sign is called string concatenation. Concatenation, it means to join, to stick two things together. So in this case, what I'm doing is I'm taking a stored value in memory location F name, and I am joining it to a string literal. So anything that is contained within double quotes is known as a string literal, and that string literal happens to be a space. I'm taking whatever's stored in the first name, I'm appending to it, joining to it the character space, and then I'm doing one more concatenation or one more join. I'm taking to that whatever is stored in L name, and the overall effect is I take the first name, I insert a space, and I add the last name, and that whole thing, first name plus last name, first name plus space plus last name, those three parts joined together, I then assign to a new memory location called name, to another memory location called name. A couple other things real quickly here. You'll notice that on some of these statements, after the semicolon, I put slash slash, and then I put in some comment. That is a comment statement. When language translation occurs, your source code is given to a compiler. The compiler takes those source code statements and translates them into binary format. That's the way it normally works, unless the source code statement begins with slash slash. If that occurs, then the compiler recognizes that that is a non-executable statement and does not translate it. So if you want to insert some straightforward English comments just to make your program code more readable, then you can use comment statements freely. And I'll use comment statements and talk about stylistically what's the best way to use them in a program. That'll be discussed later on, but right now I'm just throwing out this idea of a non-executable statement called a comment statement, one that begins with slash slash. All right, so let's take all this and try to do something real fast with it. So what I'm going to do is I'm going to write a program that will provide two text boxes, one where a user can put in their the current year, another where the user can put in their birth year, and then there will be a button, and when I click it, it'll subtract the birth year from the current year and show the person's age. So let's create a program that does something like that. I'm going to the Start menu. I'm going to launch Visual Studio. Again, I'm using Visual Studio 2010. And it works the same way with Visual Studio 2012. I get a Start menu, and I'm going to choose the option New Project. It wants to create a C# Windows application and wants to name it Windows Forms. I'm going to name this Demo Module 2. Okay, and I've got it set up so it will create it in a folder called Temp Workspace, and it's going to create a separate directory for my solution file. All that was discussed last time. This is what I want, and so I'm going to say OK, and here in a moment, like the moment has occurred, I now am in Visual Studio, and I'm going to expand this window here in the designer view, and I'm going to very quickly go to my toolbox and I'm going to put a label on. Drag it over here, stretch it out. The label has a design time property that can be changed called auto size. It's a bool data type. It's currently set to true. I'm going to change it to false. And this also has, the label has a text align property. I'm going to align it according to this graphic center. And it has a text property, and I'm going to change the text property value to current year. So I'm providing a runtime prompt to the user, and I'm going to create this a little bit smaller. I'm going to go back over here and make another change. Now the label is still highlighted, so if I change the back color, wherever that might be, back color to something a little bit more noticeable. Okay, so not terribly exciting, but noticeable. How's that? Okay, so I misspelled current. Okay, and I'm going to go back down here with the label being in focus, and I'm going to change the text, make a little editing change here, and change that to current. Click back there, fix it. Now here's a trick to speed things up. I'm going to highlight this, do a Control-C, click on the form, Control-V, and create another label with the same property values. Okay, and then I'm just going to go back in on this second label and change the text property value to birth year. Click, there we have it, birth year. Great. Okay, let me change that real quick. Okay, now I can do these things in class, make mistakes, and it's not going to be noticed, but just for a brief instance in time. I do it on the video, and I have to live with it for life, so always embarrassing. All right, so I'm going to create a text box here, drag it out. Now the text box has, again, a property that's kind of annoying called a multi-line property. Now how do I know these things? Well, I use the software enough. I've just learned it over time. And I'm going to change that multi-line property to true. And the same as before, I'm going to do a Control-C, Control-V, and move that text box up there, and then we will go back here and create a button. So scroll in my list and find a button, and I'll move it over here and change the text property to calc age. How's that? And what I'll do is, at runtime, I'll let the user put in the current year, I'll let the user put in birth year, and then when they click calc age, it's going to take what's here, convert it to integer, take what's here, convert it to integer, do a subtraction, and then it will assign the result to the title bar up here. So where it says Form 1, it'll come back with the age. That way I don't have to create another label or anything to store the age. All right, so that's my objective. I want to design this program so that the user can input the current year here, the birth year here, click, and it will calculate the age and store the result here. So the action is going to be contingent upon a button click, and therefore the program code, the C# program code, is going to be embedded in this object, button 1, this object's button click event. When I double click, it takes me to the code window, and I'm specifically at the click event method. There's the method header. Notice it says button 1 underscore click. That's the click event method associated with that button. And here's where the code is inserted between opening brace, left brace, and closing brace, right brace. And what I'm going to do is put in my first line of code, and I'm going to declare variables. Comment statement. local variables. Make it more readable. That's a non-executable statement. And then I'm going to need to create some memory locations to accommodate things. The first memory location I'm going to create is going to be of type integer, int, and I'm going to name this BYR. Okay, so it's kind of a short name, a little less descriptive than what I would normally use, but for a simple program it'll serve its purpose. I'm going to set it equal to nothing. How's that? I'm just going to declare the variable. Okay, and then the next one I'm going to create another variable called int C year. Follow that same kind of naming convention. And this one I'll go ahead and assign it something. Now I got to go back, look back. The current year is going to be in text box 1. So I want to get this correct. So I'm going to use the .NET convert object to, notice the IntelliSense that pops up, that'll be very helpful, to, and I can make this int 16, int 32, I'll go with the middle of the road, int 32 size integer, and I want it to convert what's in text box 1's text box 1's text property. Now, whenever the part of the statement appears in highlighted in IntelliSense, I can hit the tab key and it'll automatically write it for me. So that's kind of a nice, again, shortcut. Okay, so I've got B year and I've got this. Now, it thinks there's a problem here because I haven't used B year yet. I'm going to go down here and declare my third variable here, int diff year. We'll call this diff year. And I can't do the calculation yet because I don't have a value in B year yet. So I'm going to have to just declare the variable without assigning it anything. And then I'm going to actually use some dedicated assignment statements, and I'm going to let B year be equal to convert dot to int 32 text box 2 dot text, and I'm going to let diff year equal C year minus B year. Oops, I wasn't watching. B year. Okay, now at that point, when the program runs, it will get the data for C year at the time that C year is created, and then it'll have to wait for the data for B year and diff year until these two assignment statements are executed. But right now, if I were to stop everything and go look to see where things are, that calculation that provides me with the meaningful information that I want is stored inside the computer's RAM. So now I need to display it, and I told you I would use the title bar. I need to display it so that the user can see what's going on. So I will, through one more assignment statement, this dot text is going to be the target. This dot text means title bar. Okay, I'll explain more about that later. This dot text, same thing as title bar, equal diff year, but diff year in its current form stores type integer. Right now, that's not going to work. I will be assigning a numeric value to a string formatted location on the form. So built into .NET, if you need to convert something that's numeric to string, just the opposite of what I did up here with the convert statement. But if I need to go the other way, typically for display purposes, and convert something that is numeric into string, there is, for string object, anything that's string has built into it a toString method. And so I can simply say variable that I want to assign .toString, that converts it to a string format, which makes it compatible with the text property of the form or the title bar. And so there you have it. There's the program, and I'm going to run it. And when I run it, I will put in a current year of 2014 and a birth year of 1954, and click Calc Age, which will invoke the click event method, and it will do the calculation. And holy smokes, what is that? 60? That can't be possible. Well, okay, with that thought, maybe I should shut down and go take a nap or something. Old people like to sleep. So I finished this module, and I will let you look this over and view it as many times as you need to. Let me real quickly go ahead and stop the program from running and close. And now I'll go ahead and stop the program. We saw last time how to save the project. Make sure that if you do this, you save your project properly. Okay, that's it for now.